Welcome to the 11th lecture on parallel programming with OpenMP and MPI. Today we're going to cover a little bit more about advanced MPI functions such as derived data types and virtual topologies, as well as some MPI performance pitfalls. So first, let's go into derived data types in MPI. Why do we need such a thing? Why are the data types in MPI that are provided by the standard not sufficient? Now let's start with an example. Let's say that one process, the root, as we call it, reads a configuration from a file and wants to broadcast the data to all the others. So in this case, we would read something from a file and then have a couple of broadcast function calls in order to broadcast parts of this configuration, which would be here in this example, two integers, a double and an int, to everybody else. Now this is of course error prone and cumbersome. What we'd like to do is pack it all into a single broadcast and send it in one go. So that's what we want. However, it's not straightforward to do this because MPI is a library. It has no idea about the structures, data structures that you have set up in your main program. And also the API doesn't really enable such a kind of thing to make a data structure in the MPI main program available to the library. Also, you might think that you could just use MPI byte as a data type and send the structure as just a blob of data. However, this is not a solution because it sacrifices one of the main properties of the MPI definition, which is portability, including data conversion between systems with different data representations. So this will not work if we use MPI byte. So even though it may work in practice, you can do that. It's not in the spirit of MPI. A more compelling example probably is if you deal with matrices and you want to handle and communicate parts of matrices that are not stored contiguously in memory. So for example, this is a matrix in C. I've labeled the different entries of the matrix according to their offset with respect to the base address, which means each row is contiguously stored in memory in C, but not a column. If we want to handle a column of a matrix in C in MPI, this column is data which is scattered in memory. So we would have different choices here. We could choose to send each data element separately, alone, which would be hazardous because each time we do that, the message would be very short and we would be latency bound, which is the least desirable solution. It would have the least effective bandwidth for communications, and that's not what you want to do. You could manually copy the elements into a contiguous buffer and then send it. That would also be a solution. However, it's also cumbersome. It's a lot of code for such a simple thing as sending a column of a matrix. So it's quite desirable to have a better solution than that. MPI gives you such a solution in the form of data types. If you want to make a new data type in MPI, it's always 3 steps in a row. The first step is you construct the type with an MPI call, which always starts with MPI type and then something, and that something depends on what kind of data structure you want to cast into a new type. I'll come to some examples later. In a second step, you commit the new data type with MPI type commit, and you provide a pointer to this data type structure to the commit call. The reason this is necessary or defined in the standard is it gives the MPI library a possibility and option to do some pre-processing or pre-compilation steps internally to optimize this data structure layout. For example, it could figure out whether or not it's necessary to reserve a separate buffer for this data type. The third step is, well, actually, after the first 2 steps, you can use the data type in your programs as if you used a normal base type like integer or double. And then after use, if you want to save some memory, you can deallocate the type with MPI type free, again providing a pointer to the data type. MPI provides several different options of defining types, and I will cover 3 of them here today. Keep in mind that all these calls are local, non-collective calls, so it's entirely possible to define a data type only for a subset of the ranks of a communicator. However, if you want to use types, chances are that you will be using them on all ranks. So typically, these calls are done on all ranks, but it's not strictly necessary. The first type I'd like to show you is a flexible vector-like type. It's not the easiest, the simplest type that MPI provides, but is, let's say, the simplest non-trivial type that can really do something for you. It's initiated with the call MPI type vector. It takes a couple of arguments, which I will go into detail here with the help of an example. So what we want to do is we'd like to send a part of this contiguous vector, and this part should consist of two blocks of 3 elements. Each element is an MPI int by itself, so it's a base type. And after each block, there's a gap of 2 elements, another block, and another gap of 2. This kind of selection out of this vector can be parameterized by 3 numbers: the count, the block length, and the stride. The count is the number of contiguous blocks we'd like to select. The block length is the length of a single block. And the stride is the offset from one block start to the next block start. Now it's easy to see here in this example that here the count is 2 because we have 2 blocks of 3. The block length is 3 because 3 is the number of elements in each block. And the stride is 5 because that's the offset from one block start to the next block start. And then of course we need to specify what the original type was, and in this case we select MPI int. These are the data we need to supply to MPI type vector in order to define a new type, and what we get out of it is the new type because we supplied with a pointer to an object of type MPI data type. Now here's what we would do in practice. We define the data type object, MPI data type NT. We call MPI type vector with these arguments, 2, 3, 5, MPI int, and the address of the data type object, and then we commit the type. From this point on, the type is usable in our programs. We can use it in send and receive operations, and we'll come to an example later. At the end, we may or may not free the type with MPI type free. There are 2 quantities or 2 parameters that you may be aware of, or it's useful to be aware of when dealing with such types, and this is the size and the extent of a type. The size of a type is the accumulated size of all the elements that are part of the type. In our case, it would be 6 integers, so it would be 6 times the size of the old type. If the old type is a 4-byte integer, it would be 24. So this is all the data that comprises the type, not including any gaps. The second parameter that characterizes the type is the extent. The extent is the distance from the first byte to the last byte of the type, including any gaps, and, at least by default, not including any gaps at the end. So in our case, it would be 8 because it comprises the 3 integers of the first block, the gap of 2, the integers of the second block, and then it ends here because the rest is just gaps. So in our case, the extent would be 8 times the extent of the old type, which would be 8 times 4, 32 bytes. We'll come to size and extent a little bit later again. When using such types, there's a big caveat. If you concatenate such types in a send operation, this can lead to unexpected results. So for example, in the type we previously defined, the flexible vector type, if we use it in a send operation and we want to send 2 of those objects in a row, then this is the result. By default, any gaps at the end of the type are not considered when using it multiple times in a send operation. So the gap is missing. This can be corrected for, but the default operation, or the default behavior, is that the gap is ignored. You have to keep that in mind. A general advice in this respect is to always define types in a way that makes it unnecessary to specify more than one object of the type. Now, I've already talked about size and extent. there's functions in MPI to get hold of the size in bytes and the extent in bytes of a data type in a message. First call is the MPI type size. We can supply it data type now as a copy, not necessarily as a pointer because it will not be changed. And the size is an output parameter. The extent, on the other hand, is a little bit more complicated. The extent is the span from the first byte to the last byte of the data type. Again, we supply it with the type object, new type in this case. What I get out of it is the extent, and now usually I would say this is an integer. However, MPI has a special data type for that. It uses the MPI aint data type to store addresses in memory and distances or offsets in memory. So there's a special type for that. In other words, it cannot be taken for granted that what you get as an extent here is actually usable as an address in the base language like in C. Always use the designated MPI data type for that. What might be interesting in some contexts is also the lower bound, LB. You also get it at the same time. Lower bound is the address in memory where the data type starts. So we will see later that some data types are actually bound to a specific address in memory, and we can request that address using the type getExtent function. Now again, in our initial example where we had two blocks of 3 with a gap of 2 in between, the size would be 6 because the bare number of bytes used to store the useful information is 6 elements, but the extent would be 8 because the distance from the first to the last element is 8. Now MPI allows you to correct the problem with the gaps by changing the extent of a data type. So you can use LB marker and UB marker, and it does not affect the size or the count, but the extent of the type. Of course, also the message content is not affected. Of course, it does affect what happens if you use data type in a send operation or receive operation and specify a count that's more than 1. In that case, the defined gaps will be observed as opposed to the default behavior where the gaps at the end and the beginning will not be observed. Now, the MPI type vector type can be used very easily to implement one of the examples I covered in the beginning, namely to send a column of a matrix in C. C has row major data layout, so you cannot use a plain array send for sending a column in C. Let's assume we have a matrix of n rows and n columns. Of course, it has 30 entries. We define a new data type, nt, object, and we define a type vector that addresses this second column. Now, how do we do that? We need to know the number of blocks, which is n rows. Each block has a size of 1, because we only want to send a single column. And the number of columns, this is the distance from one block to the next, because the stride is just from the beginning of one block to the beginning of the next block, and that's exactly the length of one row in this data layout. Now, you may have noticed that type vector does not require to specify any address of a data type, which means we can use it to send the second column of this matrix. We can actually use it to send any column of this matrix just by specifying in the MPI send operation the appropriate starting address. So for example, to send the second column as shown here, all we have to do in the subsequent MPI send is supply an address that points to the first element of this column. All the rest will be taken care of automatically internally by MPI because it knows how to get hold of the remaining elements in this data type. Now, what happens under the hood, whether or not MPI will use a separate buffer to compile the message into a contiguous message, then send it, or send the pieces separately, you don't know. We can only hope that it's implemented effectively. As usual with MPI calls, with higher functions and MPI calls, you may assume that simple stuff like this is handled automatically in a more or less efficient way. So the general advice here is to actually use the data type and not compile the message in your own buffer and send it as a plain array. The next derived data type I'd like to show you is the subarray. It's created with the MPI type create subarray. Don't look too closely at the name. There's a create in here, which was not present for the vector type. The reason is that some of these type designation functions have been redone with recent versions of the standard, and there were significant changes so that the name had to be changed. So some of the type definition functions have a create in them, but it doesn't actually make a difference. So MPI type create subarray is for creating types that comprise parts of multidimensional data structures. The subarray call requires a dims argument, which is the dimension of the array, 1, 2, 3, 4, whatever. AR sizes is an array with the entries that hold the size of the array in different dimensions. The subsizes array, AR subsizes, designates what is the size of the subarrays we want to address in the different dimensions. And AR starts indicates the starting indices of the subarray inside the whole array. So it has as many entries as there are dimensions in the array. As a convenience, we can also define whether the storage order is C order or Fortran order, or in other words, row major or column major. Now, to make this all a little bit less abstract, here's an example. So this is a 2D structure, a matrix, and what you want to do here is define the bulk of the matrix. So the matrix except the outer boundary. Okay, so everything except the outer layer of elements. Of course, this particular type could also be defined using MPI type vector, but you will see the flexibility of this when you see what we're doing here. So the dimensions count is 2, of course. We have a two-dimensional matrix. AR sizes is just the dimensions of the matrix, so n rows and n columns here. AR subsizes, that's the actual dimensions of the subarray we want to address. In this case, each dimension of the new data type should be 2 less than the original dimension. So it's n cols minus 2 and n rows minus 2, because you want to cut away one layer of elements on the outer boundary. AR starts designates where in the multidimensional structure the subarray starts. And in this case, we'd like an offset of 1 from the row and the column start index. So AR starts contains 1 and 1. So this designates this as the upper left corner of the subtype. And then we have C order, so row major order, which means that the data is stored in memory row by row. MPI needs this, of course, to get hold of the correct elements here. And the old type is just the original type of the data elements in the matrix. So with these arrays and numbers, we call MPI type create subarray. We commit the type, and then we can use it, for example, in a send operation. Now, of course, we need to supply an address. In this case, the address will be address of buffer of 0, and this would be the actual upper left corner of this structure. If we actually specify anything else, the result would be incorrect. It will not fit the sizes and offsets we've designated here. So in this case, as opposed to the vector data type, always specify the starting address of the original multidimensional data structure. So as I said, in this particular example, you could just as well have used MPI type vector, but in multiple dimensions, also where the gaps at the boundaries are not always the same, we will immediately see that the subarray type is much more flexible and powerful than the vector type. The third type I'd like to introduce is MPI type create struct. This is actually the most flexible type. With that, you can take an arbitrary collection of variables scattered through memory and make them a new data type. It requires a count, which is just the number of elements we'd like to put in there. Actually, the number of blocks we'd like to put in there. The block lengths in an array. The length of the array is count. Displacements, which designates where the different blocks starts. And since these are addresses or offsets, we need the data type MPI int. We need, of course, the original types of the different block elements. And this is an array called here types of type MPI data type. and what we get out of it is the new type. So here's a little example. In this case, we have two types, the green one and the blue one. The count is therefore 2. The block length is 1 for the first type and 3 for the second type. The displacements array would hold the addresses, the starting addresses in memory of the first block and the second block. And it's easy to see that with this flexible layout, you can define any collection of arbitrary data elements in memory and make it a new type. This is extremely flexible. Now there's a little bit of a caveat with displacements array. These displacements can either be displacement in bytes with respect to a given base address that you have to specify in the MPI send call, or it could be absolute MPI addresses. So you have a choice here either to attach the absolute addresses of your block starts to the type, which will make the type less flexible. Okay, it will make sure that this type can only be used in this process where each single element of the type has a specific address, and this address is fixed within the type. If you use displacements, it's a little bit more flexible. You can specify a base address, and then the displacements are actual displacements. So the address is not in the type. This is the basic difference between using displacements and MPI addresses. Both options are at your disposal here. Now, speaking of addresses, I've already told you that MPI defines a special data type, MPI aint, to handle addresses. And there's a call, MPI get address, that lets you obtain the MPI address of a location. So the first argument is that location, which is just a pointer in the base language, like in C. And what you get here in the address output argument is the MPI address as an MPI aint. Again, I cannot stress this enough. Don't just assume that this is an actual address. This is something that could be an opaque data structure. You don't know how it's actually organized. And first and foremost, you're not allowed to do arithmetic with it. You might assume that this is the case, but in MPI it's not allowed. Of course, sometimes you need to do arithmetic with addresses, for example, to calculate the offset from one data block to another one in order to set up a data type. And for that, MPI has two service functions, MPI aint diff and MPI aint add, in order to subtract and add MPI addresses. The most important one, arguably, is MPI aint diff, which takes two MPI addresses and yields their difference as an MPI aint. Here's a little example for that. We have an array A of 100 doubles. What we'd like to do is calculate the offset in memory from element 50 with respect to element 0. Of course, in C you know what the result is, but MPI has its own way of handling addresses, so we need to learn how this is done in MPI. What we need is 3 objects of type MPI aint, A1, A2, and disp, and A1 and A2 are used in MPI get address calls to get hold of the addresses of A0 and A50 just by supplying the actual base language pointer as a first argument and the address of the aint object as a second argument. So after these two get address calls, we have the two MPI addresses of those two elements in A1 and A2, and then we'd like to calculate the difference. This is done with MPI aint diff, and the result is in disp. Usually the result would be 400, which is just 50 times 8. Okay. Keep in mind that if you look into the standard, you're not allowed to do this subtraction directly. You have to go through the aint diff call to do that. Also, if you'd like to calculate an address of something using a base address and an offset, you have to go through aint add to do that in MPI in order to get reliably correct results. Now, for some calls, you use absolute addresses. For example, if you have bound a MPI type create struct to absolute addresses, then when using such a data type in an MPI send call, usually you need an address as the base address of the buffer. However, in that case you don't, because the addresses are already bound to the type. So in this case, if absolute addresses are encoded into the data type, use MPI bottom as a buffer address. So here's a quick summary of what we learned about derived data types. Data types are a flexible tool to communicate complex data structures in MPI. There are many options. I've only selected a couple. So here are the most important calls. MPI type vector is the second simplest beyond the simple contiguous type. We have seen create subarray, which is more flexible for multidimensional arrays and can create subarray of multidimensional data structures. Create struct, which is the most advanced. We learned about type commit and type free that allow you to commit the type and free it. If the type uses a lot of memory, then if you don't need it anymore, you can free it. We learned about get address, which obtains the address of a type in terms of MPI addresses, and MPI A and add and MPI A and diff are used to calculate with these addresses. And finally, we can get hold of the extent and the size of a type with the two service functions MPI type get extent and MPI type size. There are many more useful features of the derived data types. For example, there's a type contiguous, a type indexed, and some more. You can look into the standard to learn about those. What I haven't covered, which would be self-explanatory, however, is the matching rule. So if you have a program that handles derived data types, the matching rule is that a send and a receive match if the specified basic data types match one by one, regardless of the displacements. Keep in mind that if you define something like a create struct in several MPI processes, the mutual offsets and base addresses of these elements could be different from process to process. So something like a struct created on one process is not portable directly to another process because addresses, or at least offsets, are encoded into the data structure. However, the matching rule doesn't say anything about displacements. The displacements are disregarded. All that needs to be done is matching the basic data types one by one. So the order, the type, and the length of the blocks should be the same, and then the matching takes place. The correct displacements at the receiver side are automatically matched to the correct data items in that case. So to keep this short, it's done as expected. Okay. The second part of today's lecture deals with virtual Cartesian topologies in MPI. Cartesian topologies are a convenience feature of MPI, which means you don't actually need this feature, just like you don't actually need collectives in MPI. However, it makes your life much easier for certain types of problems. Especially if you deal with multidimensional problems and Cartesian domain decomposition, virtual topologies provide a convenient process naming scheme to fit the communication pattern of the program. It simplifies the writing of code, so there are some functions in it that you would have to write yourself if you would have to do this by yourself. And in some contexts, with, of course, the implementation allowing, it could allow MPI to optimize communications between processes. So here's an example. Let's say we have a simulation volume, a 2D array of 4,000 elements by 3,000 elements, and we cut it into chunks of 1,000 by 1,000 elements. And these 1,000 square element chunks should be mapped equally, or should be mapped to 12 ranks in a 4 by 3 grid. So this is a very common setup, and of course the details may change. They may not all be the same size because the overall size of the data structure may not be a multiple of the subdomain size in either direction, and all sorts of complications can occur, but this is the basic setup. Now, what the virtual topology does for you is it lets MPI map the ranks to the coordinates in this process grid. So for example, you can ask questions, which rank goes where? So which rank is this part assigned to? And who is whose neighbor? So if I'm this rank, who's my left neighbor, who's my right neighbor, who's my bottom neighbor, who's my top neighbor? And is there a periodic boundary condition so that if I'm this rank, is my top neighbor maybe this one down here? Okay, these are all functions that MPI provides for you. What it does not do for you is map the actual array segments to ranks. So you have still got the freedom to map the actual data to any rank in the MPI program that you prefer. So this also leaves some optimization space, which we're not going into here. So here we're dealing only with this virtual setup of this topology, who is whose neighbor in this grid. So here's how we create a new Cartesian communicator. I should add that we're dealing here only with Cartesian virtual topologies. MPI actually has a more flexible way. It can establish any topology, not just Cartesian. Any neighborhood relation can be mapped to MPI. But to keep things simple, we're restricting ourselves here to Cartesian topologies. So the call is MPI cart create. And what it does it creates a new communicator. And the Cartesian topology is encoded in this communicator. If you want, then the MPI convert communicator that you start out with when you start an MPI program has a simple topology, which is just every MPI rank has two neighbors. The left neighbor is rank -1, and the right neighbor is rank +1, and that's it. It's a simple one-dimensional topology. The MPI cart create lets you create more complex topologies in a Cartesian setting. It needs the old communicator as a first argument, the number of dimensions of the process grid. There's an array dims. It has n dims elements, and dims of I specifies the number of ranks in dimension I. So in our example from the previous slide, dims, the dims array would contain the numbers 4 and 3 because we're dealing with a 4x3 process grid. There's another array called periods. Periods specifies in index I if dimension I is periodic. So if period contains a 0, it means non-periodic. If it contains a non-zero element, it means the dimension is periodic. So this influences the neighborhood relations, whether or not this process will have an upper neighbor. If the y dimension in this grid is periodic, then the upper neighbor of this rank will be this rank down below here. If the dimension is non-periodic, then there will be no upper neighbor. And there's an argument integer reorder, which could be 0 or 1. It allows the ranks of old com to have a different rank in cartcom, meaning that the order of the ranks could be arbitrarily chosen by the MPI implementation. The rationale behind this is that if the MPI implementation knows about the network topology and how processes are mapped to the network, then it may be able to optimize the process placement, assuming that predominantly next neighbor communication takes place. I should add that few MPI libraries provide this facility, so most do nothing if you specify any reordering here. So here's an example from our example from the beginning. We have a 4x3 process grid. So n dims would be 2 because the grid is two-dimensional. The dims array would contain the numbers 4 and 3. The first dimension has extent of 4. The second dimension has an extent of 3. Periods would be 0 and 0, specifying that there's no wrapping around. So the boundary conditions are open. There's no upper neighbor for process number 3, for example. Reorder is set to 0, which means the ordering of the ranks should be preserved. Okay, and what this gives us here is a mapping from the original MPI rank 0, 1, 2 up to 11 to Cartesian coordinates pairs. So 0 would be 0, 0, 3 would be 0, 1, 6 would be 0, 2, and so on. What changes if we change the first element of the periods array to 1? Now, nothing changes with respect to the second dimension, dim1. It's still open, but the first dimension will then be closed, meaning that the right neighbor of process 9 will be process 0, and the left neighbor of process 0 will be process 9. The same happens in the other two rows. So this is the consequence of the periods entry. Now, of course, we need some convenience functions to deal with that. The first function answers the question, who am I in the grid? So what is my rank in the new communicator? And of course, you can use the standard MPI com rank call. To do that, you specify the new communicator, cartcom, I call it here, and the output argument is the rank, your rank in the new communicator. The second question we have to ask is, where am I in the grid? So I need a mapping from my rank, or any rank for that matter, to coordinates within the grid. This is done with MPI cart coords. It needs the communicator as the first argument, the rank I want to request. This could be the rank of the calling function, of the calling rank, but it could also be any rank. So any rank can request the coordinates of any other rank, of course. Maxdims is just the length of the last array, coords, which is the third argument of this call. In coords has maxdims elements, and it receives the coordinates for rank. So this function provides a mapping from the rank to the multidimensional grid if the grid has 3 dimensions, coords has 3 elements, and the 3 entries in coords give us the coordinates along the 3 dimensions of this rank in the grid. So this function maps a rank to the coordinates in the grid. The third function maps grid coordinates to a rank. So it answers the question, who is at that position? It needs the communicator, an array that holds coordinates as an input argument, and a rank as an output argument. So if your there's a special feature, if your process grid is periodic in some direction, then you can provide any positive number as a coordinate. It will automatically be wrapped around and mapped to the valid range. If you provide an invalid coordinate for a non-periodic dimension, then the result is erroneous or undefined. What you get is the rank of that process in the process grid. Here's an example. Again, we have our 12 processes arranged in a 4x3 grid with column major numbering, and the process coordinates begin at 0. Process number 4, or rank number 4, has Cartesian coordinates 1, 1. Rank number 11 has Cartesian coordinates 2, 3. Now, of course, if we want to communicate in such a grid, and very often you want to communicate with your direct or next-to-next neighbors, then what we'd like to know is who's our left neighbor, who's our right neighbor, bottom and top neighbor, or neighbor in any direction for that matter. Also, who's our next-to-next neighbor in any direction. MPI provides a function for that, and it's called MPI cart shift. It needs the communicator, the direction, which is the dimension we want to look into, a displacement. So this is the positive or negative offset we want to look into. So if displacement is bigger than 0, we shift in positive direction. If it's smaller than 0, we shift in negative direction. So here we can answer the question, who is our neighbor in positive y direction 2 neighbors apart? Okay, and then this would be 2. And negative y direction would be -2. Source rank and dest rank are the output arguments for MPI cart shift, and they return the requested ranks as input, so they can be used directly into MPI send receive calls if you wish to do so. Of course, you don't have to use them for send receive, can be used for anything, but this is what you want to supply to an MPI send receive call if you want to implement some kind of a ring shift in one dimension. So to make this more clear, here's an example again of 4x3 process grid. The grid is periodic in the first dimension and non-periodic in the second. And each process has an int value that should get shifted. So here is our process grid in the column major layout as shown on the previous slide. MPI cart shift is supplied with a communicator. 0 is the first dimension, so the 0th dimension, the x dimension. 1 means we shift by 1 in the positive x dimension, and we get source and destination arguments. So what we get is source and dest as an output, and we can use them directly as an input to MPI send receive replace in order to provide a ring shift in this direction. This means process number 3 will receive from 0 and send to 6. So in this picture here, we only denote the directions or the ranks from which data is received. So number 3 received from 0. Number 0 actually receives from 9 because we have a periodic dimension in periodic behavior in the first dimension. So 0 receives from 9, which is denoted by the 9 here. Now what happens in the other dimension? Here with this card shift, we supply 1 as the DIMS parameter, so we're now addressing the other dimension, the y dimension. The shift is again 1 and we get source and destination. So in this case, we start with the original process grid, and now we know, since the dimension is non-periodic, 0 does not receive anything. So there's no one to receive from, and the designated source rank will be preset automatically by MPI card shift with MPI proc null. So which means that the MPI send receive replace will work as intended, and every process that doesn't have anything to receive will have MPI proc null as its source parameter, or if it doesn't have anything to send, it will have MPI proc null as its destination parameter. So everything is taken care of, and you don't actually have to change the code significantly when going from a non-periodic to a periodic dimension and vice versa. So for non-periodic dimensions, MPI proc null is returned on boundaries, so you don't have to think about that twice. Alright, so much for the advanced MPI functions. We'll probably cover 1 or 2 more in the lectures to come. I would like to conclude today's lecture with some typical performance pitfalls that you are bound to come across in MPI. Probably the most popular one is implicit serialization and synchronization. Even though your MPI program may look like everything is nicely parallel, there are instances or situations where your program is automatically and invisibly serialized in a specific setting without you knowing about it. So here's an example. We have a linear shift in an open chain, which means each rank issues a send and a receive in this exact order: first send and then receive. Only the first rank only does send, and the last rank does only a receive. So we're implementing an open chain here. Now, of course, this will work, and in the light of what I said about blocking point-to-point communication, you know what could happen if everybody calls the send function first. If this were a closed loop, there would be a danger of deadlocks, because the send could be actually a synchronous send, and then everybody would call send and we'd end up in a deadlock situation. However, the chain is open, so there's no danger of deadlocks, because there's one rank, in this case number 5, which only executes a receive. And this means it can match the send on rank 4, so the communication can take place, which again means the receive on rank 4 can be posted and so on, and the communication can ripple through this chain, and there's no danger of deadlocks. However, the performance of this whole thing, of this whole operation, depends crucially on implementation-specific parameters in the MPI library. So, for example, is buffered or synchronous MPI send used? Or if the MPI send is synchronous, is the protocol used of the eager or rendezvous type? And we'll come to this in a minute. So here's the best case scenario. The best case scenario is that there's buffering in place, so that all MPI send calls operate in a buffered send mode, and everything is stored at the local rank, for example, and then the send can terminate and immediately call the receive. The process can immediately call the receive. Now this means the MPI send returns directly, the receive is posted, and can immediately match the send from the previous or from the lower rank. So this means overall the send-receive operations can be overlapped if the network is conveniently non-blocking, if it's bidirectional and non-blocking. So this is the best situation. It happens usually if the message size is small. Now here's probably the the worst case scenario. I call it worst case scenario 1. It happens if the send is implemented as a synchronous send with a rendezvous protocol. What does rendezvous mean? It means that the send operation blocks until the complete message has been transferred. And it's completely at the disposal of the MPI implementation to do that. So you can have a valid MPI implementation that implements all the MPI sends with synchronous sends and using the rendezvous protocol. So the send returns only after the message has actually been transferred. This is allowed. Now what will happen, of course, the send-receive pair on ranks 4 and 5, they will match right away, no problem there. However, the send on rank 3 can only actually start when the receive on rank 4 has been posted, which will not happen until the receive on rank 5 is finished. So there's a shift between the receive on rank 5 and rank 4, and so on, which means the receives cannot overlap in time across ranks. So this is a totally serialized communication process. It will be the worst case scenario in this example. So the conclusion is all data transfers will be serialized. The second worst case scenario is when the synchronous send, the send is actually implemented as synchronous send, but uses the eager protocol. Eager protocol means that the message may be transmitted to the receiver without a matching receive being posted. The data is put at a buffer at the receiver side. Now, whether or not this occurs depends on many factors. There have to be enough buffer space available at the receiver side to actually take the message. There also has to be some software infrastructure or hardware in place to actually make it possible to transfer the message without the receiver actually calling MPI receive. So many unknowns here, but it is possible, and there are implementations which do that. Now, if that happens, all we need to do is a handshake. So the send must be posted. There must be a handshake with the receiver side, and the message can be received, then the send can be terminated. And the receive can be posted and so on, which means we have a partial overlap of the receives. There's still the ripple effect. Yeah, so there's still some shifting between consecutive receives, but there will be overlap if the network is sufficiently non-blocking. Now, what could we do to mitigate or to eliminate such effects? Now, a very good idea in this respect is to reverse the order of send-receive calls, even in odd ranks. So, for example, if we keep the send-receive order on rank 4 and 5, we could reverse it on rank 3. So, calling the receive first so that it can match with the send on rank 2 and so on. This way, we can complete the whole operation in 2 time steps, and we have a lot of overlap between receives. So this could be a very interesting solution if the algorithm allows for it. A second solution would be to use non-blocking I-send, I-receive pairs. And in this way, we're telling the MPI library we want to communicate messages in parallel, just by specifying here's a couple of I-sends, a couple of I-receives, do whatever you need to make it happen. It also provides for asynchronous data transfer if you do it right. I'll come back to that later. So this is very attractive. And first and foremost, if you combine outstanding sends and receives in a single wait call, then there is the option, and MPI libraries actually do that, there's the option of overlapping sends and receives at the same time. So the effect will be very similar to what we see here in this figure. Or you could use MPI send receive or MPI send receive replace. So under the hood, if you look into implementations with our open source, you will see, for example, that MPI send receive is implemented as MPI I-send, MPI I-receive, MPI wait all sequence. So in this case, the coding becomes very simple, but there's no asynchronous data transfer because send receive, well, it's a blocking call. So when it returns, we can use the buffer right away. So there's no option of overlapping communication with useful work. The last pitfall I'd like to describe is network contention. And you have to be aware that contention in a modern computer system is ubiquitous. It's everywhere. On the network level, it may occur in several flavors. So for example, very common, multiple processes on a node can try to use the network interface at the same time. So usually in modern networks, a single communicating pair of processes on different nodes can utilize the network bandwidth to almost 100%. So if you have a single pair communicating and there's a long message, then this long message is usually transferred at wire speed. Now, if that happens and a second pair of ranks wants to communicate, there will be contention, and the network bandwidth per process will go down linearly if it is the case that a single process can achieve the full network bandwidth. So this is the standard case for contention, multiple MPI processes wanting to communicate with the outside. Of course, there are also many cases where this doesn't hurt. For example, if those multiple processes don't want to communicate at the same time. If the communication requests are skewed in time, you may not see any contention. However, many programs are some kind of the bulk synchronous type where everybody computes and then everybody communicates, and then this kind of contention will easily occur. Contention may also occur if the network topology is not fully non-blocking. So if the bisection bandwidth per node decreases with increasing compute node count. So I covered that a little bit in the last lecture. Examples are torus networks or oversubscribed fat tree networks. So even if you don't have multiple MPI processes who want to communicate outside the node, you could still have contention because the network does not provide enough parallelism to sustain the number of messages flying around. And third, I also covered that in the last lecture, even if you have a fully non-blocking network, you can still have contention because you may have non-optimal routing algorithms. If you have static routing, so the path a network package takes from one node to another node is fixed, then there are always patterns which force contention on certain connections. You cannot avoid that. Only with perfect balancing across the network you can avoid that. Or if you optimize your routing tables according to the needs of the application that's actually running. The communication pattern, or MPI call, that's most vulnerable in terms of contention is the MPI all-to-all. Because in MPI all-to-all, every process wants to talk to everyone else at the same time. And you know there are supercomputers today with hundreds of thousands of nodes, and imagine what happens if you want to do all-to-all in such a system. So in general, there's a recommendation, don't do MPI all-to-all, period. Try to get away without it. Now, another pitfall that's quite common is the assumption that non-blocking MPI calls are actually asynchronous. So one motivation is that they are called non-blocking. It's actually a misnomer, or at least an unfortunate choice of terminology. The intention of using non-blocking for communication overlap is as follows. You want to communicate something to a different process, and while it's being sent, you want to do useful work in order to overlap the communication overhead with useful work. So you issue an MPI ISEND with a request handle and a buffer. You do useful work, and of course you do not modify the buffer because that's forbidden by the standard. And when you finish doing your useful work, you come back and do an MPI wait and finish the request, hoping that in the meantime the message has been transmitted. In a perfect world, this works well. The useful work takes longer than the communication, so that when you return from your useful work, the communication is over. And secondly, the non-blocking MPI call actually implements asynchronous data transfer. However, in practice, if you read the standard, it does not say anything about asynchronicity. So the standard does not guarantee asynchronous transfer. Now you can look at MPI implementations and you will see that asynchronous transfers is supported by many of them, but only in certain contexts, not always, only under certain conditions, and it's certainly not reliable in an arbitrary context. So how do we test for asynchronicity? How do we check whether or not an MPI implementation supports asynchronous data transfers. And of course, there's a whole industry of benchmarking, which I will not go into here. I will show you a simple benchmark that you can use to test a part or to answer part of this question. So what we do here is we do some work for a configurable time, which is configured here with this delay parameter, while a message of size count is being received or sent. So in this case, we're using MPI iReceive to kick off a message transfer of size count. We do some work, which has a defined time delay. We measure the time, after the work is done, we wait for the request to complete, and then we measure the time this whole thing took. And we print the overall time and the delay time. Now what happens if overlap occurs? If overlap occurs and we start with very small delays, the overall time will just be the communication time. And as long as the delay is smaller than the communication time, the overall time of the program will be constant. Now, as soon as the delay becomes longer than the communication time, the overall time will rise. So that's a typical pattern. If you plot the overall time of this piece of code with respect to the delay time, if overlap occurs, we'll have a flat phase and a slope. If there's no overlap, we'll have a slope right away. Now for this particular case, I've done the experiment on the MAGI cluster at RZE, which has an OmniPath interconnect from Intel. I used Intel MPI 2019 Update 8 and a rather large message size of 240 megabytes. Now these two curves were obtained on different conditions. The default behavior, this is the blue curve, the default behavior is no overlap. We see here that as soon as we start increasing the computation time, the delay, the overall time also goes up. We have a linear rise in overall time. This means there's no overlap between computation and communication for these parameters. However, there's a tuning knob in the Intel MPI implementation that allows us to switch on asynchronous progress. You can set the environment variable MPI async progress to 1. If we do that, we get the red line, and clearly, as long as the delay is smaller than the communication time, the overall time stays constant, which means we do have asynchronous progress. We have overlap of communication and computation, and a corresponding speed up of the overall program. Now, some general remarks. This was an experiment done on a specific system with a specific network with a certain version of the MPI library and certain other settings. Overall, this is a moving target. MPI implementations change all the time, and if you compare, even if you compare within one vendor, comparing Intel MPI 2017, 18, and 19, you get entirely different behavior across different MPI calls. So whether or not the MPI library is able to overlap depends on many factors. For example, whether you communicate within the node or between nodes, depends on the message size, which network layer you are using, and so on. So it's really a moving target. The good news is MPI implementations provide tuning knobs that allow you to influence this behavior. And this MPI async progress shell variable is just one of many parameters the Intel MPI provides, and other MPI implementations have similar parameters. So if you rely on asynchronous progress, look closely at the documentation of your MPI library and find out whether asynchronous progress is actually supported. Here's a little summary of MPI performance pitfalls. The first advice is always observe possible synchronizing properties of MPI calls. And if you don't know what's going on, always assume the worst possible behavior. And that may not get you to the most well-performing programs, but it will certainly keep you away from the worst mistakes. Even if a deadlock does not occur, performance may be severely impacted. So you may not observe a deadlock as a severe problem, but if you actually study the scaling properties of your program, you may see that communication may be less than optimal. Network contention is a fact. If network communication is a significant overhead factor in your program, you have to study how your program reacts to contention. And maybe network contention is a big problem, and then you can think about it and see whether or not you can mitigate it. Most large-scale networks, even with expensive supercomputers, are not entirely non-blocking for reasons of cost. There's just no way to build a fully dynamically routed, non-blocking, fully connected fat tree network on a supercomputer with 1,000,000 nodes. This is not feasible. And finally, non-blocking MPI communication, even if it sounds good, is usually not necessarily asynchronous. So study the possible tuning knobs, and if there's a tuning knob that gets you over the threshold to the asynchronous behavior, employ it. Thank you.